Thank you so much for joining us. We will be hosting half of the crew on Zoom and half of on Remo. So hopefully everything works out. But thank you everyone for your patience. We are super excited to introduce our upcoming panel, the future of tooling in the APAC region. So I'd love to invite John, who is our moderator. Hey, John. Along with our other speakers to join. All right.
Okay, we have everybody now.
We do.
Excellent. Sam, you're all mic'd and ready?
It appears so, yeah.
Good.
All right. I'm just going to need, John, do you mind actually sharing your screen for the presentation?
Oh, sharing? Yeah, I can do that.
Wonderful.
The entire screen?
Yes.
Yeah?
Let's see. Yeah, can you share the APAC meetup slide deck?
Oh, that one? Okay,
yes.
Hang on. Where is that? Okay. It's a bugger because it's in another. I'm not seeing it for some reason.
Okay, no worries.
Kentaro isn't in as well, just for your info.
Oh. It's okay.
Oh, Kentaro's gone. Yeah, I can't say, it's not seeing it.
Okay, no worries. Kentaro, do you mind turning on your camera? That would be lovely.
Yes, can you see me now?
I can see you. Okay, great. So we're just going to do a first introduction. You guys can all probably see my slides.
Nothing as yet, Janet.
Oh, you can? Perfect. Okay.
We can't.
John, feel free to take it away.
Hang on. Okay, so up to me now, Janet?
Yes.
Okay, firstly, welcome everyone. And listen, we have a great collection of experts from the APAC region that have joined us for this session. This session will go through a series of questions. And listen, please feel free to use the question bar and submit any questions. We will try to get through them during this session. Each of our people that we have talking. Janet, can you share their slide when they're up? Thank you. So these are the people that we have. Sean, we have Sam, Kentaro, Vishwash, Sam Tagliar.
Yes.
Jeffrey Coe, Kentaro,
And Dr. Vishwash.
and Vishwash. Good. All right. Listen, I think what I'd like to do, Janet, is I will ask a question, and I'll ask three of our esteemed colleagues to first one to put up their hand. I think what is one of the biggest questions is, what are the benefits of using AM technology for tooling applications? So I'll put that one up for the first. And who would like to at least have first go at talking about this question?
I mean, if nobody wants to do,
Yep.
I can start. This is Kentaro speaking. If you want me to start.
Good. Yes, thank you, Kentaro.
Yeah, okay. so I am from DMG Mori, machine tool producer, and I would say, so my company, we are selling additive manufacturing machines from the powder bed fusion technology and directed energy deposition technology. And first of all, I would say that, of course, there's so much potential now still for finding new ways of producing tooling or repairing tooling with additive manufacturing. So, of course, I think the biggest advantage is the chance to innovate in the field. And from my side, I would say I'm quite specialized on directed energy deposition and tooling, and I can say that the interesting thing about directed energy deposition and tooling is that you can repair tools, but you can also build new tools, and you can create tools with which are made out of multi materials, so different alloys put together. So the big benefit is that you can improve tooling in the whole life cycle, not only the new tools, but also repair and also maybe changing tools at a later stage. So, and this can improve the whole energy consumption and the whole life cycle waste of materials. So I think these are huge potentials for this technology.
Thank you, Kentaro. Could I have a little bit more input from one of our other panelists?
Yeah, sure. Hi, my name is Sean. I'm the general manager for Create 3D. We provide 3D printing technology in Singapore and Vietnam. So one of the works that we have been, besides working with several companies, we've also worked with many small, medium enterprises in Singapore that are not traditionally associated with 3D printing, like in the food industries, etc., packaging, etc. And the benefits of AM allows them to really explore a new dimension, upgrading their workforce. I think it's important that they see that there's another way of doing what they've been traditionally manufacturing. So that out-of-the-box thinking allows them to further innovate on their processes in what they're doing. So I think the flexibility with AM does help in a lot of companies to think of new ideas that traditionally they've kind of been boxed in from their day-to-day work.
Yeah, thank you, Sean. Does anyone else like to put in a comment in regards to the benefits of using AM for tooling applications?
Yeah, John, you probably can't see me on the screen, I suspect.
Yeah.
I will say something. I guess that in the areas where I work, the biggest advantages are that you can do things that you could never do before, and getting the benefit of the technology to design molds in a better way that we could never do before is a huge advantage. I've been, after 40 years in this industry and trying to design dies with optimum handling of cooling and heat transfer between plastics and metals. It's a dream to be able to handle new designs that were never possible before and obtain process advantages that we never had before. So that's a real revolution in the design of dies.
Okay. So, okay, thanks.
Because it's sort of echoing.
Yeah, I know we've got a bit of an echo, mate. That's the unfortunate thing with the Zoom. Now, we notice, and you mentioned it as well, Sam, that probably one of the major benefits with doing tooling and additive manufacturing, of course, is around the conformal cooling and the benefits that actually brings in. Does anyone else want to talk further on probably what they've done with conformal cooling and how it's actually benefited the end use customer from a monetary point of view?
Sure. So I'll come in here. So this is Vishwas here from Amaze Solutions. We are a part of the ACE Micromatic Group, which is one of the largest CNC machine tool groups from India. And AMAZE is the additive manufacturing wing of the group. So we've been working and providing 3D printed solutions for a lot of tooling manufacturers. Some of them include plastic injection mold manufacturers. We have die casting producers, die casting die manufacturers, and also for some of the pattern manufacturers in terms of making them in a short time. So to just add what benefits that conformal cooling. So conformal cooling is definitely the biggest advantage that we've seen that manufacturers have been benefiting. Not only has it been able to help our customers reduce the cycle time because of the reduction in the cooling time, but we've seen a lot of our customers come back to us and tell that they've been able to get better surface finish or the part that they get out of the mold, either the plastic injection molded part or the die casted part. They're getting better results out of it. So I'd like to bring in here, not only are we looking at advantage from a cycle time reduction or a productivity perspective, but also in terms of rejection, reduction of the rejections, and especially in terms of, for example, die casting applications. We've had customers who come back and tell us that who've shared information in terms of how the number of blowholes and rejections because of blowholes in their die casted parts were reduced significantly, because they were able to use mold inserts which had conformal cooling on them. So I'd say on an average, we've seen people report at least between 5 to 8% or 10% in some extreme cases is the rejection rate in a die casting application. So when it comes down even by about 1% or 2% because of conformal cooled dies, I think it gives a significant advantage to the end use application, especially when you have few thousands of them being casted on a daily basis. So that I feel is a key advantage that people are able to benefit directly from the conformal cooling or the AM application. John, I think you're muted.
Me buddy at any stage. I think, thank you very much, Vishwas. I know from conformal cooling and some of the benefits that have been attained through some of the molding, through the polymer molding practices, I mean, up to 45% in benefits. So it does have a long-term benefit if you're going into series production, utilizing additive. We know additive is not a cheap substitute for general tool making, but it does add a huge amount of benefits. I suppose when looking at those benefits, you know, from your point of view, when would be a good stage for a company to look into additive manufacturing for the future of doing their tooling? Jeffrey, maybe this could be up to something that you would like to add in too.
Jeffrey's just...
Sorry?
Jeffrey's unmuting. Jeffrey, do you have comments?
Okay, sorry, I just mute. Okay, this is Jeffrey here from DMAX. Basically for toolings, when we plan to start AM's implementations, you know that AM's for toolings normal cycle is that we have RFQ. After RFQ, we are doing this so-called technical discussion or TFM. Then we kick off two fabrications. Then we do for tool and trial and qualifications. So at any stage, actually we can implement AM at any times. But today in the markets, most of them or most of the tool makers in China, mostly is that after they completed the two builds, they found there's a lot of trouble with the tool. Then they start to think of using AMs to implement, to improve their tooling quality or part qualities. So in my view is that in the future, this kind of trend will change. It's just that, remember during the 90s when we start to use hot runner system. So a lot of people that actually initially were very so-called reject to use hot runner system because it's expensive and long lead times. And this is the same scenario as what we are seeing now for AM in the tooling industry. But in the last few years in China, we are seeing there's a lot of change here. So we are seeing more bigger company start to implement AM in the initial stage. So this will change and will drive more tool making company to use AMs moving forwards. So I think that's trying to, and first of all, of course, individual company will have to understand what's the benefits of AM, which is a few guys we haven't already mentioned the benefit of AM. On top of that, we have to use the software to do the simulation to justify for AM investment, because AM at a tool manufacturing stage is actually incurred additional cost. The saving of the AMs is on the downstream where you come to production, where you help to improve your production yield, shorten the molding cycle times. You can produce a parts in a certain capacities, at a shorter lead times. So the benefits, if we want to implement the AMs in the tooling organizations, we have to look at the total picture, which is the whole benefits of the whole projects. So this is my inputs, for those who consider or haven't used AM before. Yeah, John.
Yeah, thanks, Jeffrey. Listen, for those who are probably sitting in the audience, can some of you talk about some of the materials that are now being offered at the moment, currently, and then we might have a little bit of a discussion on what materials people know that are being worked on for the future. Who would like to take up the first bit on this?
I can talk about the metal industry. So from a tooling perspective, what we've seen, the most popular ones are materials like your maraging steel, which is your 18Ni 300 or 1.27009, which is widely popular because of its properties that they offer. Then H13 is a good printable material, of course, with its own small concerns in terms of printability, but that again is a good tooling material, especially for high hardness applications. Then we have other materials like D2, which are emerging. Then we have newer materials also like P20, which are being researched, where people have been trying to offer that as a material that can be printed. And of course, from a pattern application, we have aluminum, which offers a good material from to develop or print a pattern for specific applications, which can be further taken to making die casting or other further processes in the die casting or other foundry applications. So these are some of the most popular materials that are there today for tooling manufacturing.
John, it also has to be said that there are quite a few proprietary versions of those steels coming out. A number of companies are producing their own versions of H13 and their own versions of maraging, claiming better printability. So there's obviously that these companies are looking at developing the market and improving the performance of the materials or the metals in the tooling. So I think that's a very positive thing for the industry, that there are companies out there doing that. Yeah.
Sam, probably leading on from that, what do you see as the developments occurring currently with hot worked tool steel powders for AM?
Well, look, there's a number of companies out there that are saying that they've developed their own version, tweaks on H13, which is more printable, because it's well known that there are problems with printing H13.
Yeah.
Especially cracking of the material. So there has been a bit of a general trend towards miraging, but in order to address these problems with H13, I can at least think of two major companies that are developing, actually three major companies that are developing their versions of H13, which they claim are more printable than the standard.
Uh-huh. So just another thing, when we're talking about all these materials and that and the metals that we're using, is there any dimensional constraints that are being seen to be becoming evident in doing tooling?
Yeah, John, I think there has been a trend towards the smaller machines like 280s.
Yeah.
But we're getting up to the 400s and the 500s now that would be looking at tooling in the future because it always has been a bit of a barrier to the size and the cost. Obviously, as the part gets bigger, the cost goes up. So I think it would be nice to see a trend towards bringing that cost down and making larger inserts for tooling.
Yep.
Hopefully that's what the future will hold for us, that we'll be able to make bigger and cheaper parts of high quality.
Okay. And listen, while I'm talking to you all, just to let the audience know too that more than welcome for the audience to participate by putting forward any questions that they feel that they would like to see answered by the panel.
Well, the good thing, John, is if you click on the Q&A tab, you've got 4 questions already lined up.
Well, okay, hang on. Q&A, here we go. All right, well, number one, tooling or tool manufacture is still quite a traditional industry, as we were all still well aware of. I mean, that's my background. I was a tool maker for quite a few years. What are the challenges now to the adoption of the AM in the industry? Would you guys like to sort of impart a little bit of from the traditional tool maker? What are the challenges now of them adopting the AM support?
Jeffrey, you want to start first?
Okay. I think for a traditional tool making company, I think first of all they will encounter problem is on the design side. Today, most of the designer or design engineer don't have or have very few design experience on designing conforming cooling. So even they design the coolings, conforming coolings. The question is, how effective is this cooling? And they will get challenged by end customers or someone else. So over here, my personal experience is that when the first few years when we start designing conforming coolings and show it, present it to our customers, most of the time our customer will challenge us how effective is the cooling. So in conventional, most of the time you don't get this kind of challenge from your customers because most of the customers know that the conventional cooling design and there's a lot of constraints and they know that they will not have much concern. But when it comes to conforming coolings, whereby the design, when you look at some very complicated designs, it's very, very fancy design. So normally over here, we actually use simulation software to simulate the heat transfer, the temperatures difference within the insert, the different temperatures, to show the effectiveness of the conforming cooling. So this is the first challenge that for a company when we start to trying to use AM for the cooling. The second part is come to machining of the AM. You know that after prints, there's a stock allowance on on the inserts, whereby we normally we keep about 0.5 mm to 1 mm per size. And normally when we come to machining, the two shops have to have a kind of practice that when you come to deal with this kind of AM inserts, when you're taking a reference to this kind of inserts, you have to take from center instead of from a single site reference. So our experience is in China here, we have few company when they started use the first AM inserts, they just screw up and they actually had to remake the insert again because of they are not get used to it when taking the reference on the insert for AM inserts. The third point, I think is the most important point, is the maintenance of the tool or the AM tool. So, because of this conforming coolings, the design was the cooling was moving at irregular shapes. So it depends also this kind of steel material you use. But in China, for example, the quality of the industrial water was actually pretty bad. So it means that the inserts, if the water will stay inside the inserts, it will get corroded very fast. Within a very short period of times, you get corroded, and once you get corrosion, the water channel will get blocked. So the user of this kind of AM toolings, you have to know how to take care of this kind of. So make sure after every move trial, we have to do a thorough cleanups on the water channel, and also to do a water flow rate checking on the tool. That means before and after, so that to ensure there's no blockage in the conforming cooling channel. So, and this is, I think, currently in China, the tool making industry, the so-called the working disciplines was not so good. So we always had to spend a lot of time to educate the user, how to make sure that they keep a good working practice on the AM tooling. Yeah.
Okay.
Kentaro, do you have anything you'd like to add?
Yeah, I mean, of course, I think the issue with the adaptation of additive manufacturing in tooling is that most people know about conformal cooling, but I mean, this is not the only technology out there, and I think there are many benefits, and it's constantly moving forward. So I mean, as John already mentioned, then that there are different materials and even new materials coming up all the time. So it's very, I think, of course, from the customer side, it's very difficult to follow this constant change. So it's very important to push the information from the vendor sides and from the service company sides for the adaptation, because I mean, to follow this from the customer side is really difficult. So I think for our audience, I think the most important point is, of course, to talk to the service bureaus and to the machine vendors or the material vendors about new technologies regularly, because there are new solutions really all the time.
Yep. Yeah.
And Sean, since you serve the SMB market, any challenges that you can highlight?
Most of the SMBs are very cost sensitive.
Yeah.
So as a result, AM is traditionally a more expensive technology compared to traditional manufacturing. So most of the question here is they always ask for a cheaper solution, because they are not able to push up their selling price. So in the SME context, the cost benefit analysis, kind of when they evaluate AM, it has to be made clearer to them, and as well as how can they monetize that AM technology. I think this is the difficulty for most of our customers in the SME industries, because they do not know how to sell AM as a benefit in their day-to-day business. I think that's one of the major issues that we see.
Yeah, I think you're right, Sean, in a lot of respects there. I said, you know, if we have a look at it, and I think Jeffrey said the same thing in regards to that. I think it's one of these things that if companies could see the benefit of doing a traditional mold and then analysing an AM mold, they would see the benefit. It would do its own justification. I mean, you could run that through a very simple program like Mold Flow or one of those around the cooling side of it, because we know with conformal cooling and that it actually also reduces the problem of distortion in the end product to quite a big degree. So I think for educating manufacturing industries, I think that the one way of educating them is looking at, all right, if we do this traditionally, this is our traditional tool design, we analyse that and then analyse another one that's done around AM with conformal cooling. I think one of the biggest areas that we are still missing in on is around the design. And I think the next question which has come is talking about the value chain of AM, which part, material, machine, design, or is there something else that's the most challenging in terms of cost? We know equipment is a challenge, it's a cost. Material is a challenge, although material prices fluctuate from wherever you're going to get your material from. I mean, if someone wants to add to this, please, from your point of view, what do you believe is one of the cost challenges that we're having in AM? Is it a designer? Is it the actual machine that you're going to purchase? In a lot of cases, a lot of companies are only going to be going to a service bureau to actually get their inserts produced. So please feel free, jump in, someone.
Yeah, so I'll add a small perspective here. So in our little experience, what we've realized is other than a few exotic materials, the cost of material is anywhere between 15 to 30%. And the remaining is largely the equipment cost and your post-processing cost based on how critical the end part is. So what is really important is for someone to realize how the equipment or the utilization of the equipment. I mean, equipments are around the similar prices, but what is more important is how do you get the best out of the equipment? How productive is your equipment, so you make sure you utilize it to the minimum extent, and of course how critical is the end part from a post-processing perspective, which can be accommodated in the design stage itself. So if the part has complex geometries which would need, say, 5-axis machining, then that adds significant amount of cost because you're making one-off parts and you have a lot of risk associated with it. So that's what we see is how the cost probably would get distributed. So it is material, of course, is important. It does add value, but I mean add to the cost. But more important is what happens during the printing and after the printing is what consumes most of the cost. And I'm sure there's also a factor from a rejection perspective to be able to factor in because of printing which did not go right. So that's something that will also add to the cost.
Yeah, yeah. Listen, Sam, this could be a good one for you to chime in on. As we know, Amero has done quite a bit in the tooling industry, both polymer and die casting. Please feel free to come in and give your considered opinion.
Well, I think that there's a couple of things along the value chain which need to be looked at from a cost perspective, and that's the simulation of tooling to incorporate, for example, conformal cooling is actually not a cheap exercise in itself. And also the acceptance of that simulation as being real is something that has to be worked on. And the other thing is that really the machine cost and the machine time for printing is costly. So productivity of the printing machine itself and the sizes that can be printed and the productivity are high as in terms of targets for improvement in the future. And I'm very confident that as time goes on, those things will improve. But we always see it with new technology that it takes a while for the enhancements and the improvements to occur. We've seen it in many other technologies, particularly the tool-making industry has been faced with these types of challenges in the past. And I see that I would think that the big driver has got to be the process owners, the people that actually have got the processes, the casting processes and the moulding process. They're the ones that get the benefits. So they're the ones that have to push for the technology. Tool makers can talk to their customers and do some technology transfer, but it's from both ends, push and pull. But really push from the casting company, injection molding companies, is where it's got to come from, because they're the ones that are going to get the benefits and have the need. For the tool makers, it's just another way of manufacturing. It's just another arsenal, a tool in their arsenal of machines that can produce tooling. So eventually, when we get the cost down, and it's already started to happen, there will be tool makers that will purchase an AM machine like in the past they used to purchase a CNC machine.
Correct.
And have it as part of their arsenal of manufacturing machines that they can use.
Yep. Yeah. I think that, there's a question that's coming up that I think has been asked by Alex, which we'll go into shortly. I know Aditya has just indicated, considering the Indian additive manufacturing ecosystem, how metal printing is cost effective for Indian industries in terms of metal powder cost, operating costs, etc. Maybe Vishwas, this is an area for you to make a comment on.
Sure. So as I explained earlier, from a costing perspective, India is a huge, has a huge tooling industry. A lot of manufacturing from a plastic injection molding to die casting happens here, and there's diverse opportunities. So, and more importantly, India is a very cost-sensitive market. So we don't have large manufacturers with deep pockets who are willing to invest that extra bit for both design as well as getting the parts printed. So that is a matter of concern, which is why, though it's growing in demand, it could be much better because people are yet to see how the intangible benefits can be quantified, which is the real challenge here. But like you rightly said today, there are people, there are softwares which are able to do a lot of things beforehand. Before we go ahead with printing, we are able to identify the benefit, especially from a cycle time perspective. What sort of improvement can we predict? What sort of reduction in cycle time or the cooling time can be seen? Which, when you do the math, you'll be able to identify what sort of savings are we able to envisage in the whole process of printing, thereby justifying the investment both the design as well as manufacturing would bring in. So, but from a material perspective, if I have to say, like I said, the costing today, we have fortunately materials available locally too. So we have specialized manufacturers of powders locally. So especially for the tooling industry, I don't think so. The material cost is a significant contributor because qualified them for different types of applications, and we ourselves have used powders from certain sources which are giving us good results. So that is something that is quite low in terms of cost. And from an equipment perspective, yes, that adds significant value. I'm happy to share that we ourselves have come up with our own metal printer. So we've have a large format metal printer, which is a production ready one with a large build volume. So that's typically made suitable for inserts and dies of large sizes to be printed at a much higher productivity level. So this is what we are looking at, which could be a good answer, which could convert a lot of the conventional ones with complex geometries requiring to be printing dies and inserts for specific applications into conformal cooled 3D printed mold inserts or mold parts.
Interesting, because probably one of the areas you may be working in with the H13 steels, but Maruko-san has asked regarding H13 for tooling parts, post-hardening heat treatment does it require anything special of a technique or know-how?
You want me to get that?
Yeah, you can have a go at that. I would expect that maybe Sam might also have a go at that one.
Sure. So H13 is a difficult material to print, as Sam earlier mentioned. So we have a lot of cracking issues. It needs a little more of tweaking and playing around in terms of the parameters and the strategy of printing. But we've done quite a bit of H13. In fact, one of our good projects also, which is there in our intro slides, is what we've done for not only die casting, but even for a forging application, where customer has seen a good advantage from a tool life perspective, and also with the conformal cooling, they're using it for as a lubricant insert port, where the graphite which is required for forging is being used. So we've done quite a few of these H13 parts, and we've been able to crack the cracking issue with with, of course, quote unquote, with its own bag and baggage of loss of productivity, maybe a bit of different types of strategies. But yeah, the heat treatment perspective, there are standard cycles which have been identified, which have been developed for heat treating them in terms of both stress relieving as well as in terms of age hardening them to the level of hardness that is required for specific applications. So based on what the application is, people have their hardness levels and properties that have to be established. So accordingly, the cycles have been established so those results can be achieved.
Okay. Alex Kingsbury has asked a very pertinent question, and that's, how does the surface quality of AM tooling compare to traditionally made tools? What surface finishing techniques are used, and how does the polishability compare between materials? I mean, from my background, be it P20s or H13s, P20s you tend to nitride, then you polish them. H13s, of course, are like a through hardening steel. Polishability is still good. But listen, I'll put it out to you guys. I mean, who prints inserts, and then what issues do they have in surface finishes with doing polishing and that at the end result?
John, maybe I give some inputs on these finishings. So
yep.
We come to AM's two fabrications on the surface. Actually, it's quite similar to conventional machinings. You did not have to pay special attention to it. The finishing can be as the best finishing we can achieve for AM material is SPI A2. This is so far we have achieved. It also depends on the insert geometry. Sometimes we do able to achieve up to SPI A1 mirror finishings. Not a big large surface area, especially for round parts, for which you have a high chances to achieve SPI A1 finishing. And also depends on, because right now over here, 70% of our material we are using standard steel grades, which is we call it CX or conventional steel, we call it ASAP Corex. You can get it from ASAP, or you can get it from a lot of providers for this kind of materials. And my personal opinion is that we most of the times we will recommend our customer to use Corex material because it's a standard steel grade material, which is we found that is better than using American steel. But on another side, one of the weakness of this material is the hardness, which is a bit low on the hardness. So the conventional Corex material, the hardness, maximum hardness we can go is 51 HRC. So for AMs instead using CX materials, normally hardness is around 46 to 48 HRC. So we feel that in the future, most of the tool using AMs, there's a trend that most of them were using these CX materials. When I started this AMs business in 2016, the first 2 years was almost 100% we used American steel. On the third year, we start to implement this standard steel CX. And today, this is my 5th year in this business. And we are seeing there's 70 to 80% of this inserts or the requests from customers are CX material. And this CX actually, we see there's a lot of benefits. And one of the biggest advantage is standard steel grades. So this is my input, which we see. And we also see that we have customers from Europe and in North Americans, they will start to requesting us to use standard steel material. And point of view is that eventually American steel probably is only suitable for die casting tool because of the hardness. But for plastic injection toolings, probably most of the user will start to use CX materials, and then this will give as good polishing as good as conventional steel material.
Okay. Anything?
John, on the polishing for die casting tools.
Yep.
Often the requirement is not as high as injection molding. Therefore, it's never been an issue that with both Mirage or H13, from the printed surface to polish or for some final machining and then polishing to the levels that die casting requires. It's never been an issue really at this stage.
Okay, no, fair enough. I think one question I'd like to ask you all, are there any unique cases that you feel that are impactful and noteworthy that you'd like to share at the moment?
Yes, I mean, this is Kentaro speaking from DMG Mori. I would like to maybe describe a very interesting case we did with a company in Germany called DGH Group. As DMG Mori, we developed a with only conforming cooling channels, but also to build die casting molds out of 2 different alloys. So the inside, the core of the tool is made out of a copper alloy that has a high heat transfer rate, and only the surface is made out of tool steel. And by using combining conformal cooling and this bimetal material, the cooling effect of the tooling becomes very high. And the customer, so the customer DGH Group, they work in die casting, and they they compared all kind of different technology tooling, And the result was that by using this conformal cooling and bimetal tools, they were able to reduce the scrap rate of this production by about 3.36%, or about 3.5%. And of course, if you are only producing prototypes, this is not such a big number. But if you are in mass production, 3.6% scrap rate reduction is really huge. And this means this will mean about 180,000 euro of scrap reduction per year. And that means they produced about 600,000 parts a year, and that a reduction of 20,000 scrap parts. And this, I mean, the important thing is, of course, there's a economical value, the 180,000 euros cost reduction. But at the same time, this will also mean a reduction of about 80 tons of CO2 output, or 80 kilowatt hours of electricity. That this kind of new type of conformal cooling can bring big benefits also for, of course, economical way, but also for the total CO2 or carbon footprint of this production.
Good.
Yeah, that's an example I would like to. Yeah, I mean, of course, if anybody wants to know more about this, we created a whole presentation about this topic, which, of course, I can share.
Has anyone else got anything they'd like to share? I've got one last question here, which has come from Aslun. As additive manufacturing continues evolving in aerospace and medical device industry, he'd like to understand AM development, what's happening around the shipbuilding, defence and renewable and wind energy and any other industries. So have any of you been working in around shipbuilding or defence or renewable with AM and tooling?
Yeah, so for DMG Mori, we have been working quite a lot with in the US with the defense industry. Mm-hmm. And of course, this is the certain parts and the details of the parts we are not able to share. But of course, there are a lot of very large parts and very high duty parts. And in that field, of course, because of the high production costs, there again, DED technology is quite a lot utilized, because the parts, if you are able to repair them, the cost reduction is really huge. And especially also in the defense sector in the United States now, especially there's quite a big emphasis on the space field. Of course, any or improvement of parts is really crucial for not only for the cost but also for safety and effectivity. So of course in defense, biggest growing industries. For shipbuilding, I think this is also another topic, large part, which is very difficult thing.
Yeah, yeah. No, well, I know that companies such as BAE and Boeing and Rheinmetall are all working in the area of AM, not necessarily around tooling, though. And of course, we know with the armed forces here in Australia, they've been working with AM too, with frontline exercises with AM, but not necessarily around tooling. Thank you very much, gentlemen. Janet, I think our time has hit the mark, has it not?
Yes, it has. Thank you so much, everyone.
No, thank you, everyone. It's been great having you all involved.
Yeah. Any last key takeaways, Jeffrey, Sam, Sean, or Vishwas that you want to share?
From my side.
No, not at this stage. Thank you for the invitation, and yeah, we hope that it can facilitate networking in the future.
Yes, definitely.
Speaking of networking, we know this is a very long event, and
Yeah, thank you very much.
wonderful. We invite everyone to the virtual networking floor. If you still have a couple of times left, we do have extending it to 30 minutes more. So feel free to jump on in and get connected. If you're not able to connect with someone, feel free to go through the chat and take their contact info and reach out to them via LinkedIn or email, so you could further the conversation. We also had a chance to put the slide deck for our wonderful panelists today, so you can have a better understanding of what they're working
Yes. Thank you,
on.
Jenny.
So feel free to download that, study it, and hopefully they can also help you in your tooling journey. Thank you,
Yeah.
everyone, for your time. Really appreciate you
Thank
all.
you.
Jeffrey.
Thank you,
Jen,
Jenna.
Thank you.
Thank you
for
very
all
much.
your effort. Thanks, guys.
Thank you. And
Thank
on
you.
behalf of the APAC Additive Manufacturing Meetup, this could not have been possible without John Koff from CNC, Kitty Wang from 3D Science Valley, Aditya from Indian 3D Printing Network, Alex Liu from ASTM International COE, as well as Wataru Nishimura-san from Link 3D. Thank you very much. And we also thank all of our other speakers earlier on, Hiro Maroko-san from Marubeni Information Systems, and as well as Mun-Chun from Materialize. Thank you very much, and hope to see you
Thanks.
at the next APAC AM meetup.
Thanks, Jenna. See you guys.
Thank you.
Yeah.
Thank
Bye.
you, guys. Thank you.
Bye.
Thank you. Bye.
Thank you.
Bye-bye.
Bye.